We're going to jump into a couple of days of graphing now. And what we're going to do is we're going to use our calculators to aid us in graphing some simple graphs and then make some generalizations about those graphs that we find and go to a form of graphing in which we don't need to use the calculator to help us. So for this first graph, we're going to graph the absolute value of x. I don't really need a calculator to do this, so I'm just going to go ahead and grind this out. I've got a little xy chart I'm going to make, and in this case I have x is here, y is here. It gets some positives, -2, -1, 0, 1, 2. Absolute value of -2 is 2, -1 is 1, 0 is 0, 1 is 1, 2 is 2. Plot those points, and you'll notice that the graph looks kind of like a V. It goes linearly in both directions, and we'll call this point, for lack of a better word, a vertex. Point where it kind of bounces. Now, if I were to take and graph y equals x plus 3, I'm going to plug in those same values and notice what happens. Again, we'll do this without a calculator because it's really not that difficult at this point. -2, -1, 0, 1, and 2. And I plug in a -2, take the absolute value of that, that's 2, plus 3 is 5. -1 gets me a 4, 0 gets me a 3, 1 gets me a 4, and 2 gets me a 5. So you'll see now that plotting these points, I also get a very similar looking graph. In both directions. Let's do another one. And absolute value of x minus 4. Pick these same points, -2, -1, 0, 1, 2. Plug in -2, get out a 2 minus 4, which is -2. Plug in a -1, positive 1 minus 4, which is -3. 0 gets me -4. 1 gets me -3, and 2 gets me -2. Graph those, and you'll notice, once again, these graphs are all looking the same. The only difference is where the vertexes are. So then let's move over here. And now we have y equals x minus 2. Let's go ahead and use -2, -1, 0, 1, 2 for my x, and we'll find our y again. So in this case, plug in a -2. -2 minus 2 is -4. Take the absolute value, that's 4. -1 gets me a 3. 0 gets me a 2. 1 gets me a 1. And 2 gets me 0. So if I graph this, we're going to first of all notice that, hey, this doesn't look anything like the previous graph that I had. It's a line almost. And that's not making a whole lot of sense because all my other absolute value graphs look like some kind of a V. Let's do this. Let's add a couple more points. Let's go 3, 4, and 5. And if I do that, plug in 3, get out of 1, plug in 4, get out of 2, plug in 5, get out of 3. Well, notice now what happens. Now my graph looks exactly like the other graphs that we had. So something else is going on here. Look at the previous graphs that I had. Look at where the absolute value was. And look at where the numbers added and subtracted were. those numbers were on the outside of the absolute value sign, whereas in this problem, we have a number inside the absolute value sign. That's got to make some kind of a difference. Let's check and see. So for the rest of these examples, we're going to use a calculator to get through the graphing a little quicker. So let's get our calculators on. We're going to type in the absolute value of x plus 5. So to do that, I hit the math button. I go number, and there's my absolute value. Hit the x plus 5, close my parentheses, and then I'm going to hit zoom, and number 6, which is going to graph it in the standard window, or a negative 10 by 10 for both the x's and the y's. And here's my graph. Now you'll notice that this graph has moved over to the left a total of 1, 2, 3, 4, 5 spots. And then let's just take a look at the table real quick. Now in this table you'll notice that I've still got it set on my ask feature. Here it is. I'm going to change this to automatic, so I'm going to move down and move that blinking cursor over by hitting enter. And now I'm going to go look at my table again. And now you'll see I have things automatically filled in. Since it moved back to 5, I'm going to move this table back to negative 5. And you'll notice that when I move over 1, I've gone up 1. When I move over 2, I've gone up 2. And when I move over 3, I've gone up 3. Likewise, on the other side, move over 1, up 1, over 2, up 2, over 3, up 3. And if I take and graph that now, let's pop these points in. Here I have negative 5, 0, over 1, up 1, over 2, up 2, over 1, up 1, over 2, up 2. There's that check mark that I've been looking at. And look at all the other patterns that I have from my other problems. Go back to the previous problem. There's over 1, up 1, over 2, up 2. Let's go back another example. Here's over 1, up 1, over 2, up 2. Let's go to our next problem. Over 1, up 1, over 2, up 2. I've got the same pattern happening every single time. It's just my graph has been moved. Let's take a look at another example. Now in this case, in the previous problems, I had additions and subtractions either to the outside or the inside of the absolute value. Now I have a multiplication. I want to take a look at this graph. And instead of using, well, I can use a half. Doesn't matter. So we'll go to our y equals again. We'll take a half. So I put all my fractions in parentheses. So there's a half. Want to hit the absolute value, which is math, num, absolute value of x. Close that. And now I'm going to take and graph that. You'll notice in this case that this thing bounces, but my shape is entirely different. It's much wider than it was before. In fact, if I were to pick a table for this, and I go negative, or x is here and a y is here, and I go negative 2, negative 1, 0, 1, 2, I plug in negative 2 and I get out a positive 1. Plug in a half, or plug in negative 1, I'm sorry, and I get out a half. 0, 0, plug in 1, I get a half, and 2, I get 1. So now you'll notice I'm here, 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 and here. Notice I've gone over 1 and up a half, over 2 and up 1. So my pattern has kind of changed at this point. My graph's gotten wider. And my bet is this half has something to do with it. Let's do one more. And you'll notice this time that I have 3 times the absolute value of x. I'm just going to plug in some numbers once again. Here's x and y. -2, -1, 0, 1, 2. And we're going to see if this gets wider or something else happens, if it moves like it has before. Plug in a -2, I get out of 6. Plug in a -1, I get out of 3. Plug in a 0, I get out of 0. A 1, I get out of 3. And a 2, I get out of 6. When I graph this, notice what's happening. This graph is noticeably steeper, skinnier, I don't know how you want to call it, but it's definitely changed. But my vertex is at 0, 0. So we've got something going on. There's got to be patterns happening. And in fact, there is. All absolute value graphs can be written in the following form. F of x is equal to a times the absolute value of x minus h plus k. F of x is the same as y. So a in this case functions as a slope. If I look at all my previous examples, let's take a look at the slope from this vertex. Up 3 and over 1. Up 3 and over 1. Now notice in this direction, it's a positive and negative since we're talking absolute value. So up 3, back 1, there's a negative slope of 3. Up 3, back 1, negative slope of 3. Let's go to the previous example. Here's a slope, rise of 1, run of 2. Rise of 1, and I go back 2. So I have a slope of a half in this case. Go back one more. Notice my a value, in this case, equals 1, and my slope is up 1 over 1, just like it is up 1 and back 1 in this case. So going back to our general formula, a acts as our slope, or m. H talks about a horizontal translation, which means the graph is moving to the left or to the right, whereas K talks about a vertical translation. So one important thing to notice is that the H follows a subtraction sign. This is really important. And what it means is that whatever number follows the subtraction sign talks about the way the graph is going to move. Now let's look at our previous examples once again. So in this case, we had an H value equaling 2 because a 2 followed a subtraction sign. Therefore, my vertex moved to the right 2. In the next example, though, you're going to notice that there was no subtraction. But if I was to make a subtraction, I'd have a minus 5 equals a positive 5. So H in this case was a negative 5, and my vertex moved to the left 5. K follows an addition sign. So outside of the absolute value was a negative. So if I wanted to make that a plus, a negative 4, K equals negative 4, and thus moves down 4, which it did. M, once again, or the A value, was 1, so my slope was up 1 and over 1. Notice when I go back one more, and K was equal to 3, my graph moved up 3. So now let's kind of put this all together and not use a calculator, not plug points in, but try to graph it based on what we know, and then plug a point in to check. So here's a really difficult problem. If we were to pick x and y values for this, this would be difficult. However, we know that this number multiplied by the absolute value is my a, which is negative 3 over 2, which is also my slope. We know that the number following an x inside the absolute value, also following a subtraction sign, is my translation number. So H is equal to a positive 6, which means my vertex moves to the right 6. And then following this plus sign is my k value. So k equals 1. Therefore, if I move over to 6 and up 1, I'm getting that vertex point on my absolute value graph. And then from that point, I have a slope of down 3 and over 2. So if I go down 3 and over 2, that's one part of my graph. If I go in the other direction, down 3 and over 2, that's the other part of my graph. And without picking any points, I seem to have graphed this absolute value function. Just for fun, I'm going to take this point of -8, or positive 8, sorry, and -2 and plug it in to see if it checks. So if I take -3/2 times the absolute value of 8 minus 6 plus 1. In this case, I get a 2, so that's -3/2 times 2 plus 1, which is -3 plus 1, which is -2. And sure enough, that point checks. So without plugging any points in, I was now able to graph this absolute value function. All right, now we're going to switch gears a little bit. We're going to write the equation of an absolute value function that looks like this. Well, this shouldn't be too much of a jump because I know my vertex. My vertex is -3 and 0, which means this has got to be my h value, this has got to be my k value. Therefore, in my absolute value, I have x plus 3 and plus 0, because that's my k value and it's got to be out on the outside. Now I've got to look at what's my slope. I rise a total of 2 and move over 1, 2, 3, 4, 5 to get to my next point. So my slope appears to be 2/5. So therefore, y equals 2/5 times the absolute value of x plus 3. I don't need to say plus 0, I can leave it at that. Now I have to make sure the point 2, 2 checks. So let's go ahead and plug the point 2, 2 in. If I get 2 equals 2/5 times the absolute value of 2 plus 3, this better check. 2 equals 2/5 times 5, and therefore 2 equals 2. I've graphed this correctly. We're going to go ahead and do one more graph just to make sure we know what we're doing. I have an h value here of -3 and a k value of -4. Therefore, my h says I move to the left 3, my k says I move down 4. So if I go over 3, down 4, I put a dot and this is my vertex. My slope, m, is equal to 2, or 2 over 1. From this point, up 2 over 1, both directions. Go ahead and graph. And without plugging in any points, I've now graphed this function. Here's a point of -4, -2, which should satisfy this problem. So if I say, here's a -2 equals 2 times the absolute value of -4 plus 3 minus 4. See what I get out. There's -2 equals 2 times 1 minus 4, which equals -2, and it checks. All right. So moving forward, the next thing we're going to talk about is a greatest integer function. Now what the greatest integer function looks like is this double set of brackets thing right here around the x. And it says I want to graph, or the output is the greatest integer not greater than the value of the number inside this double set of brackets. So if I graph the greatest integer function, I'm going to pick some points, 2, 1, 0, -1, 0, and graph the number that's an integer, spelled that wrong, that's not greater than the integer that I plug in, then I get 2 in and 2 goes out. 1 in, 1 goes out. 0 in, 0 goes out. -1 in, -1 goes out. 2 in, 2 goes out. However, what happens if I plug in some decimals, like 1.6? What integer, when I plug this in, so the greatest integer of 1.6, is not greater than 1.6? Well, I can't say 2, so my next integer that is not greater than 1.6 would be 1. If I plugged in the number 0.2, then the integer not greater than the decimal 0.2 is actually 0. When I plug in -0.7, the integer that is not greater than -0.7 can't be 0 because 0 is greater than -0.7. This must be -1. Likewise, -1.1, the integer that's not greater than -1.1 is equal to -2. So when I graph these, here's the 0.22, 1, 1, 0, 0, -1, -1, -2, -2. The problem's going to exist where I start plugging in the decimals. At 1.6, I still get out 1. At 0.2, I still get out 0. At -0.7, I get -1. And at -1.1, I get -2. So the question is, how do I connect these dots now? Well, here's the situation. This has to be a function, which means it has to pass a vertical line test. So it looks like these two dots connect. And I can move as far as I get to this point. Because otherwise, if I put a dot at -1, -2, this would no longer be a function. So I have to move as close as I can to the point -1, -2, and then stop. And the way I say to do that is with an open circle. Likewise, I move further and further to the right here until I get really close to the point 0, -1, and stop. So I put an open circle. I move very close to +1, and right before I get there, I stop, and then at 1, my greatest integer is 1. Continue to move to the right until I get very close to 2, and stop with an open circle. So this creates what's known as a step function. Which is kind of like the nickname for the greatest integer function. I think the easiest way to take and graph these is just start picking some integers and see what happens. I like starting out at least with the -2, -1, 0, 1, and 2. And then I fill in decimals as I go. So here's my x, here's my y. At -2, the greatest integer of -2 is -2, plus 2 is 0. Negative 1, the greatest integer is negative 1, plus 2 is 1. At 0, the greatest integer is 0, plus 2, which is 2. At 1, I get 3, and at 2, I get 4. Now, let's plug in these decimals. Probably easier to start with the positives. For some reason, people understand that better. The greatest integer of 1.7 is actually 1. Then I add 2 to that, and I get 3. Let's take the number 0.2. The greatest integer of 0.2 is 0, and I add 2 to that, and I get 2. Let's take negative 0.9. The greatest integer of negative 0.9 is actually negative 1 plus 2 equals 1. And let's go negative 1.5. The greatest integer of negative 1.5 is negative 2 plus 2, which is 0. So I'm going to start graphing these points once again. Negative 2 and 0. Negative 1.5 and also 0. Negative 1 and 1. Negative 0.9 and 1. 0 and 2. 0.2 and 2. 1 and 3. 1.7 and 3. And then 2 and 4. So again, now we have to find a way to connect these, and it appears everything seems to be traveling to the right from the left, and we have to make sure we have a function. So once we get to the point negative 1, open circle and stop. Once we get to the 0, open circle and stop. Once we get to the 1, open circle and stop. And once we get to the 2, again, open circle and stop. And there's our step function once again. So here's our last example. Let's make a chart again. Starting with 2, 1, 0, negative 1, negative 2. 2 plus 3 is 5. Greatest integer of 5 is 5. 1 plus 3 is 4. Greatest integer is 4. 0 plus 3 is 3. Greatest integer is 3. Negative 1 plus 3 is 2, and the greatest integer of that is 2. And negative 2 plus 3 is 1, and the greatest integer of that is 1. Start picking decimals like 1.9. 1.9 and 3 is 4.9, and its greatest integer is 4. Let's go 0.2. 0.2 plus 3 is 3.2, whose greatest integer is 3. Negative 0.5 plus 3 is negative 0.5 plus 3 is 2.5, whose greatest integer is 2. And let's go negative 1.8. Negative 1.8 plus 3 is positive 1.2, whose greatest integer is 1. We'll graph all these points, starting with 2, 5, 1.9 and 4, 1 and 4, 0.2 and 3, 0 and 3, negative 0.5 and 2, negative 1 and 2, and negative 1.8 and 1, and negative 2 and 1. Again, pretty much the same pattern. Move to the left until you create a non-function situation, open circle. Moving to the right, open circle, moving to the right, open circle, and then moving to the right, and open circle. So, there are your examples, and I imagine there's going to be some questions, and we'll take care of these tomorrow. Make sure you solve your ConnectEd problems for lesson 9. and we'll move on from there.